Hello. Today we're going to be working two lessons today. First, we're going to do 3.4 notes on concavity and the second derivative test. And real quick on section 3.5, we're going to just do a few examples on limits at infinity. So let's start with examples from section 3.4 first. If you look here, there's three boxes here that we need to kind of go through. Another important property of a function is its concavity, and that's if it's curving. This is concave. Whoa, just a minute. Okay, if it's going concave down, it's going to look something like that. And if it's looking concave up, that's what the shape looks like if it's concave up. So we'll be deciding by looking at either, usually the second derivative, if the original graph f of x is concave up or down. So a definition of concavity here says let f be differentiable on an open interval from a to b, then f is concave up on that interval a to b if the first derivative is increasing on that interval, and it'll be concave down if that first derivative is decreasing on the interval. Now when we talk about justifying for concavity, we will use this justification as in f prime is increasing on AB if you are given a graph. So if you're given a graph to look at, this is when you would use your justification that f prime is increasing to justify concavity. So kind of make a note there that you can use this as justification only if you're given a graph. Otherwise, we're going to use the next box. Test for concavity, this is the one we're going to use the majority of the time, but not all the time. Suppose that f double prime exists for all x in the set AB. If that second derivative is greater than 0, then this will be f will be concave up. So it's going to be looking like this. If your second derivative is less than 0, then it will be concave down. So that is what you're going to highlight here, and that's what you're going to be using for justification, all right there. Okay. We will also talk about inflection points. Inflection points are basically where it changes from concave up to concave down. So let me just kind of give you an example here. Let me just kind of just draw a curve. And if you notice about right here, somewhere in there, it's changing from concave down, over here is concave down, to concave up. This is concave up on this side. So there's a point at which it changes on this particular graph, and therefore that is called our point of inflection. It is possible to switch concavity without having a point of inflection, and that is when you would have some asymptotes, maybe a graph looking like this, where you have the upper left-hand corner is concave up, the lower right-hand corner is concave down. There's no point of inflection there. There's just an asymptote. Okay, so reading for in the box that says test for inflection points. It says assume that the second derivative exists for all x in the set AB, and let C be an element of the set AB if the second derivative is equal to 0, or if that second derivative is undefined, and the second derivative changes sign at x equal to C, then you know that f of x has a point of inflection at x equal to C. Okay, so again, we're referencing the function f of x, that graph, and using the second derivative to determine that. Okay, so let's look at this first example. Determine the open intervals on which the graph of f of x is equal to 6, all divided by x squared plus 3 is concave up or down. Now, if you would like to, take a couple minutes and go ahead and use your graphing calculator and graph that so you can see what the graph actually looks like. But in this particular example, I would probably go ahead and give you a first derivative and second derivative on a quiz or a test, because I'm not going to test you on this particular question. If you can find that first and second derivative, I'll be testing you on if you can actually use that first and second derivative to find other parts of your function, of your graph. And so I'm just going to go ahead and give these to you. There's my first derivative, and the second derivative is going to be negative 12 times the quantity 3 minus 3x squared all over x squared plus 3 quantity cubed. Okay, so interpreting this, I need to find where it's concave up or concave down. So I really don't need that first derivative for finding concavity. I just needed it to help me find my second derivative. So what I'm going to do is look at my second derivative and see what makes the numerator or denominator 0. So first of all, what makes the second derivative undefined? I'm looking at that denominator. Is there anything that's going to make that denominator 0? There's nobody here to answer my question, so I'll have to answer it myself. And the answer is no. There's nothing in the denominator that will make that 0. Looking at the numerator, what would make the numerator 0? So my second derivative is equal to 0 when x is equal to, do you guys have it? Plus or minus 1. So I'm still going to do my little number line charts. Okay? And I'm going to put -1 and 1. And I'm going to substitute that into the second derivative. So I'm going to pick numbers between -infinity and -1, and then plug it into the second derivative, and just see if I'm going to get a positive or negative. So if I plug in, say, -2 into the denominator, it's always going to be positive. And if I plug it into the numerator, that -12 is negative, so you have to remember that. And then if I plug a 2 into the parenthesis, that's going to be negative. So two negatives multiplied together will be a positive. Picking a number between -1 and 1, I always pick my favorite number, 0. So plugging that into the denominator, it's still going to be positive. The numerator, the -12, I have to remember the -12 is negative. Plugging in a 0 into the parentheses, I get a 3, so I get a negative times a positive, which is a negative. And do the same thing if I plug in a 2, I'll get the same thing that I got when I plugged in a -2, so that would be positive. Okay, so all we're doing is finding out when something is concave up or concave down. So we've got positive and negatives for my second derivative. So here we go. I have f is concave up. F is concave up on the intervals from -infinity to -1, and again from 1 to infinity. Why? Now, it didn't really ask for justification, but I'm going to practice by putting this in. All you have to say is because f double prime of x is greater than 0. And then we can switch to f is concave down. So you look on your graph, when is your f double prime negative? And that's going to go from -1 to 1. Why? Because f double prime is less than 0. Okay? Again, remember you can pause and go a little bit slower if you need me to stop for a little bit so you can get caught up. I'm moving on to example 2. Example 2 says to find the points of inflection. So I am going to, first of all, find my first derivative. This one's not hard to find. You just bring your 1/3 down in front. Is that a 1/3? No, actually that's a 5/3. I can't see it, sorry. 5/3 down in front. X is now raised to the 2/3 because I'm going to subtract 1 from that exponent. Then I'm going to take my second derivative by multiplying my 5/3 times my 2/3 to get my 10/9. X is now to the -1/3. And then I'm going to go ahead and write that as 10 over 9x to the 1/3, just so I can see that that x is really in the denominator. Again, to find a point of inflection, I have to make sure that my second derivative is changing signs, because sometimes it does not. I look at this and I say, okay, what makes my second derivative 0 or undefined? And we all can see that that is 0. So I'm going to plug in a 0 into my number line here. And if I take into my second derivative and plug in, say, -1, I'm going to get a negative number. Plug into 1, I'm in a positive number. So I can see that my second derivative changes signs, which is one of the stipulations. Go back and look at the box, the test for inflection points. What makes a second derivative 0 or undefined? That's our x equal to 0. And we need to see when our second derivative changes signs. So I have a point of inflection. Let's do a little summary here. I have an inflection point at, if the x value is 0, plug it back into the original to get the y value, and I get that to be 0 because f double prime of x changes signs at x equal to 0, and f double prime of 0 is undefined. You have to put both of those down to figure out, or to justify your point of inflection. Now, did it say to justify on this one? No, it did not, but I'm going to practice that because they will ask you that on the AP exam. Okay, moving on to the next page. The next page is the second derivative test. I'm not a real big fan of this because sometimes it doesn't work, but when it's helpful is when the derivative is very easy to find. So let's look at this. Assume that f of x is differentiable and let c be a critical point. We're going to evaluate that second derivative at that critical point. If that exists, then this is what we're going to do. If that f double prime of c is greater than 0, we're going to have a local minimum. If that second derivative at that critical point is less than 0, we're going to have a maximum. And if it's equal to 0, this is what I don't like about it. It's inconclusive, and therefore you have to go back and use the first derivative test anyway. So let's think about this. The reason why we can use this is I am looking at if my second derivative at that value is greater than 0. If my second derivative is greater than 0, that means it's concave up. So my critical point is going to be occurring then right down here, so you see it's going to be a minimum. Looking at this part right here, if my second derivative is less than 0, I know I have concave down. My concavity is concave down. Since it's a critical number, we know it's going to be possibly a max or a min, so it's going to be up there at the top, so therefore that would be a local maximum. So that's how that second derivative test kind of works. That's a nice little visual for you. Okay, so here we go. Let's use that second derivative test for example 3. I need to find the first derivative because I'm going to analyze the critical points. So that means I need to find if I have a relative max, relative min, or neither. Okay, so here we go. Let's do first derivative to find the critical points. I'm going to get from my first derivative my 6x squared plus 6x minus 12. Now I need to see what makes that first derivative equal to 0. So I'm going to factor that. Factor out a 6, I get an 6 times quantity x squared plus x minus 2. And I'm going to do one more time of factoring that quadratic, so I get x plus 2, x minus 1. There it is, all factored. So what are my critical numbers there? What makes that 0? My critical numbers are -2 and 1. Okay, so let's go ahead and use the second derivative test. Let's see what we can find out here. So I'm going to do my second derivative by looking at my 6x squared. So my derivative of that is going to be a 12x. Derivative of 6x is 6. Okay. So now I'm going to take my critical numbers and substitute them in. So if I substitute that in, I find my second derivative at -2. Plugging it into my second derivative, that's going to be a -24 plus 6. So I get a -18, which is less than 0. So I know that is going to be a relative max because it's going to be concave down. Okay, so I could say therefore -2. Now I'm going to plug in -2 back into the original to actually get the critical point. So if I plug -2 back into the original f, I get 20 for the y value. That is a relative maximum. Okay, now let's do the same thing for the next one. I'm going to do my second derivative at 1. I'm going to get 12 plus 6, which is 18, which is greater than 0. So I know my function is going to be concave up, so my critical number is going to be down at the bottom of that. So I'm going to plug in 1 back into the original, and I get -7 for that y value, and that would be a relative minimum. Okay, there you go. That's our second derivative test. And again, that was easy to use because finding the first and second derivatives were very quick. All right, so let's do the next one. Example 4. Analyze the critical points of f of x equal to x to the fifth minus 5x to the fourth. So again, I'm going to try my second derivative test. So I'm going to find my first derivative. And that will be equal to my 5x to the fourth minus 20x cubed. So I'm going to factor out my GCF, and I have a 5x cubed that I'm going to factor out front. So I get an x minus 4 left. What are my critical numbers? What makes that first derivative 0 or undefined? I get 0 and 4. So I'm going to go ahead and find my second derivative. So that's going to be my 20x cubed minus 60x squared. Now let's take 0. If I find the second derivative at 0, I get 0. Now look back at the top of the page. If your second derivative is equal to 0, it's inconclusive, and you have to use the first derivative test anyway. So bummer. Second derivative didn't help us at all. So what I'm going to do is I'm going to go back to my first derivative test, do my number line. My critical numbers were at 0 and 4. Plug them into my first derivative. So going back to my first derivative, plugging in, say, -1. I get a negative out front. You get a negative in the parentheses, and negative times a negative is a positive. Plugging in a +1, I get positive out front. I get negative in the middle, or in the parentheses, so I get a negative value when I multiply those two together. And then when I plug in a 5, I'm going to get a positive times a positive, so there we go. So you remember how we have to put all of our justification. So let's kind of put our justification for this just to practice, because some of you got a little sloppy on your test. I have a relative max at, if x is 0, plug 0 back into the original, so y is 0, because you have to state that f prime of 0 is equal to 0, and f prime changes from positive to negative at x equal to 0. Relative maximum at 0, 0, because because f prime of 0 is equal to 0 and f prime changes from positive to negative at x equal to 0. Doing the same thing then for the next part, I have a relative minimum at, okay, if I plug 4 into the original, I have to be honest, I threw at my calculator. I got -256 for that y value. Because, again, same thing, f prime of 4 is equal to 0, and f prime changes from negative to positive at x equal to 4. Okay, so number 5, I would like for you to get in partners. So if you could slide your desks together so you have a cross the aisle partner. If you don't have a cross the aisle partner, please make a group of 3 with the people around you. I want you to look at number 5, and I want to challenge you a little bit algebraically. Find A, B, C, and D such that, and you see that big f of x, has a relative maximum at 2, 4, and a relative minimum at 4, 2, and an inflection point at 3, 3. I want you to take a couple minutes and kind of jot down some ideas and come up with your game plan. And I want you to shut me off for a little bit so everybody can talk. So put me on pause. Then I'll come back and I'll give you some hints to see if you're heading in the right direction. And then you can work and see if you can find A, B, and C. So go ahead and do that. Pause me so you can talk. Okay, so here are my hints for you. Let's see if you're heading in the right direction. I know that I have maximums and minimums, so that means I have a first derivative that I need to look at. So I'm going to go over here and say, what is my first derivative? My first derivative is 3ax squared plus 2bx plus c. And it's talking about an inflection point, so I know I'm going to need a second derivative. So I have my second derivative is 6ax plus 2b. So if you've got those two, so far so good. All right, now I need to be able to solve for A, B, C, and D. So most likely I'm going to have to probably be doing some algebra. So that most likely means some system of equations. So let me write some down. I know that my first derivative at 2, since it's a maximum or a minimum, it has to be equal to 0. So I'm going to plug 2 in for x into my first derivative right here. And that is my 12a plus 4b plus c. I'm going to set that equal to 0 because I know that that is a minimum. Nope, it's a maximum. My minimum will be the same thing. My minimum is occurring at 4. I could write that down, but I probably won't need both of those. My inflection point, though, is at 3. So my second derivative at 3, I'm going to plug that in and get 18a plus 2b, and I'm going to set that equal to 0. So what I need is some other pairs of some equations. So looking at some other points that I know, I have a relative minimum at the ordered pair for 2. Okay. I also have a relative maximum at the ordered pair to 4. So I can write some other equations there by saying f of 2, plugging in a 2, I'm going to get an 8a plus 4b plus 2c plus d is equal to 4. Just plugging that into my original. And I also know f of 4 is my, yes, I had to get out of, oh no, I didn't. 64a plus 16b, that's not too bad to figure out, plus 4c plus d, and that's equal to 2. Okay, so I'm going to have you finish this problem together with partners, but I want you to look at this. Let me give you some hints. Take these two equations right here. I'm going to put those two together and eliminate the d. And then I will take that answer and maybe put it with this one right here and eliminate the c. Then I'll take that answer and put it with this equation right there and eliminate maybe the b or the a, really doesn't matter. But that's how you can use a little bit of calculus and a lot of algebra to finish this problem by solving for a, b, c, and d. Okay, so go ahead and finish this problem, and you can, when the majority of the class is done, go ahead and turn this video back on, and we will continue on with section 3.5. Okay, so pause for about 5 minutes so everybody can finish this up, and then we'll be back at it. Okay, just making sure that everybody got the right answer. Like I said, I put the two pink dotted equations together. I multiplied that top equation by -1. And then I got right here 28a plus 6b plus c equal to -1. I paired that up here with this equation right there, 12a plus 4b plus c equal to 0. And I multiplied one of the equations by -1 to get this equation right here, which was 6a plus 2b minus 1. And I paired that with the equation that had an a and a b up there originally, that right here, 18a plus 2p equal to 0. So I was able to eliminate the b. I got a to be 1/2, b to be -9/2 when I did some back substitution. I got c to be 12 and d to be 6. So if you didn't quite get all those, you can go back and look at this video. I'll upload it to YouTube so you can look at this video a little bit slower. Okay, on that last problem. Alrighty. Okay, switching on to 3.5 notes. In section 3.5, we're just going to do a few problems on limits at infinity. And basically, I would like to kind of go through this and show you just where our horizontal asymptote rules came from in pre-calculus. If you were to cover up the limit and just look at the fraction 20x squared minus 3x divided by 3x to the 5th minus 4x squared plus 5. In pre-calc, I'm sure you were asked to find horizontal asymptotes, and you had to come up with those rules. If the degree of the numerator is smaller than the degree of the denominator, you had a horizontal asymptote that was equal to 0. When I'm asking you to find the limit as x goes to infinity of this same fraction, I'm asking you for its end behavior. So basically, I'm asking you for the horizontal asymptotes. I'll be very honest with you, you don't have to do any calculus. You can just use your pre-calculus rules and tell me that it's going to be 0 and you move on. But sometimes we like to see, using our calculus, how can we prove that the limit is actually 0, or that the horizontal asymptote is actually y equal to 0. And this is how we do it. We take the limit as x goes to infinity, And then we look at our fraction and see what has the highest degree, what term. And I see I have an x to the fifth down there in the denominator. So I'm going to divide every single term by x to the fifth. Takes a little time to write it all out, which I'll do it since I'm a teacher. Okay, so once I divide everything by x to the fifth, I'm actually going to simplify it. And you probably could have simplified it as you went and saved yourself a little time. So this would be 20 over x cubed as the first term, minus 3 over x to the fourth. Down here in the denominator, I'm just going to get a 3 minus 4 over x cubed plus 5 over x to the fifth. Now, if I go to do the limit as x goes to infinity, I'm going to look at this, 20 over x cubed. When I do 20 over x cubed, doesn't this go to 0? Because I'm taking 20 divided by a very large number. What is 20 divided by a very large number? 0. The same thing over here, 3 divided by a very large number, or 3 over infinity, isn't that going to go close to 0? The same thing with 4 over x cubed and 5 over x to the fifth. So you're thinking of each one of those terms of individually plugging in infinity. So you're thinking of like 5 over a very large number. It's going to get close to 0. So looking at everything, I get a 0 over 3, which in fact is just 0. That's it. Okay. Example 2. Same thing, I have the limit as x goes to infinity, but here let's see if we can remember our horizontal asymptote rules. The degree of the numerator is the same as the degree of the denominator. Do you remember that rule? So you would just get what those leading coefficients are, which is 3/4. So let's kind of do the same thing we did on the last problem. Let's take the limit as x goes to infinity, and let's divide everything by x squared. So I have 3x squared over x squared plus 20 x over x squared divided by 4x squared over x squared plus 9 over x squared. So what do I get for that limit? I get 3 plus 20 over x divided by 4 plus 9 over x squared. Now I'm ready to evaluate the limit. Okay, I'm plugging in 0. So the 3 stays 3. Plugging in, no, I'm not plugging in 0. Geez, I got to pay attention. I need to plug in infinity. So 20 over infinity, 20 over a very large number is 0. 9 over a very large number is 0. So I just get my 3/4 that's left. Okay. All right. When I get to the next one, please look at that note. You might want to highlight that note in the middle of the page. Remember that the square root of x squared is not just x. It's the absolute value of x. So when we're doing the type of problems like what you see in example 3, you have to decide, when I take this square root of x squared, do I really want to put an x or the opposite of x out front when I evaluate that? And let me kind of show you how we're going to do that. All right, I look now and I no longer have polynomials divided by polynomials. All right, I have a fraction divided by a polynomial. Not a fraction, I have a square root divided by a polynomial in my fraction. Okay, so we're going to treat that a little bit differently. I have the limit as x goes to infinity. What I'm going to do in that radical is factor out an x squared. And then I get a 1 plus, when I factor an x squared out of the 1, I'm going to get a 1 over x squared. That's my numerator. Okay, here's where we have to use that little idea of the square root of x squared is equal to the absolute value of x. I look right here. This is the key on this one. You might want to highlight this. Since I'm going to infinity, when I take the square root of x squared, I'm going to get just a regular x. And then I still have my 1 plus 1 over x squared. Now, in the denominator, it would be really nice to have an x out front in the denominator as well, so I can reduce those. I don't want an x left in the numerator, because if I just put in infinity, then I really just have a limit that does not exist. And that would happen a lot. So we have to look a little bit closer and see if we can change the denominator, and we see that that can get that to be x times the quantity 1 plus 1 over x. All right, So now let's do some reducing. These two reduce. And if I plug in infinity, I have 1 plus 1 over x squared. This right here is going to go to 0. And this is going to go to 0 because 1 over a very large number is just going to be 0. So when I evaluate this, I just get 1. There it is. Okay. All right, last example here. Last example, I have the square, or no, I don't. My cube root is in the denominator. So I have the limit as x is going to infinity. In the numerator, I have x plus 1. In the denominator, I have the cube root of x squared plus 1. Now, I'm going to do something different on this one just to show you that you can. See these ones right here? When you plug in infinity, if you're taking infinity and adding 1, it really doesn't make much difference. So I'm going to put really doesn't make a difference. So what I can really do is I could really evaluate the limit as x goes to infinity of x all over the cube root of x squared, and I'll basically get the same thing. Okay, and yes, I could have done that on the last problem, but I just wanted to show you something a little bit different for that one. So this is the same as the limit as x goes to infinity of x over x to the 2/3, which is the same as the limit as x goes to infinity of 1 over. No, I don't want to put 1 over. Let's not do that. Let's just leave it in the numerator. I don't know what I was thinking. So if I subtract exponents, I get x to the 1/3 when I reduce that. If I plug in infinity, I have infinity to the 1/3, basically the cube root of a very large number. It's just going to go to infinity. Okay, therefore the limit does not exist. Okay, but I just want to show you a different method for those last two, just so you can see that you have choices. Alrighty, I am done for the day, so you have time that you can work on your homework. Hope you have a great day.